Thursday, July 16th, 5:45 p.m. Central. That's when Starship Flight 13 lifts off. But this time, something is different. For the first time ever, 20 real Starlink satellites are riding inside Starship, not steel dummies. Last flight, 5 engines failed to relight, and the booster flipped 90 degrees off course. Now, SpaceX says it's fixed. Will it hold this time? Stick around, you need to see this. Let's go back to the static fire. 4 attempts. That's what it took SpaceX to get Booster 19 through a single full-duration engine test. Not once, not twice, 4 times. The first attempt aborted on a combustion fault. The engine bay flagged something wrong and shut everything down before it became a problem. Another attempt aborted for a completely different reason. The sheer noise and vibration of the engine's firing shook sensors near the flame diverter hard enough that the system triggered an abort on its own, protecting the vehicle from a condition nobody had measured before. What most coverage got wrong was treating these aborts as bad news. They weren't. An abort means the system caught something before it turned into a disaster. Think of it like a smoke detector. It's annoying when it goes off from burnt toast. But you don't want a smoke detector that stays silent during an actual fire. Every abort on Booster 19 was the safety system doing exactly what it was built to do. The question nobody was asking loud enough: why so many aborts on one booster when previous boosters didn't have this problem? The answer is uncomfortable. Raptor 3 is a new engine, and SpaceX had never simulated what it feels like to hold down 5,000 to 6,000 tons of stacked propellant and rocket weight, because nothing on Earth outside of an actual Starship weighs that much. You cannot rehearse this. You cannot build a scale model that reacts the same way steel, propellant, and thrust react at full scale. The only way to know if the clamps hold, if the plumbing survives, if the sensors give accurate readings, is to load the real vehicle with the real amount of propellant and see what happens. That's not a design flaw. That's the nature of building something that has never existed before. Every early aircraft crashed. Every early rocket exploded. The difference with Starship is that SpaceX built an entire pad system called Stage 0, specifically so that when things go wrong on the ground, they go wrong safely and get fixed fast. When the tower breaks. The story gets physical the day after Booster 19 finally completed its full-duration static fire. The launch tower's chopstick arms were being lowered back down, and something inside the drive system jammed. Picture 2 enormous mechanical arms, each one strong enough to lift a 400-ton booster out of the sky and set it down without damaging it. These arms run on a chain system, similar in concept to a bicycle chain, except each individual link weighs 380 pounds. One of those links snapped. When a single link on a chain that size fails, the entire chain binds up. And that chain is load-bearing for 2 arms that are supposed to catch and stack the tallest rocket ever built. If the chain doesn't work, the tower doesn't work. And if the tower doesn't work, nothing flies. Not because the rocket is broken, but because the machine that assembles and catches the rocket is broken. This is the part people miss when they imagine SpaceX's operation. It's easy to picture the rocket as the star of the show and the ground equipment as background scenery. It's the opposite. SpaceX itself calls the ground system Stage 0, treating the tower, the chain, the arms, and the water system as the actual first stage of every single flight. If Stage 0 fails, Stage 1 never gets the chance to prove itself. So what did SpaceX do? They called their other launch site in Florida, over 1,000 miles away, where spare chain units happened to be sitting in inventory for the towers under construction there. A spare chain flew out overnight. Crews tore apart the broken unit, rebuilt it, and had the tower back in service the next morning. Total time from failure to fix, somewhere between 30 and 36 hours. On a component that, by the engineer's own admission, was never designed to be serviced this way in the first place. One of SpaceX's own engineers pointed out that if this exact same failure had happened on a small electric motor bearing, the fix would have taken an hour. Instead, because of the sheer scale of everything involved, a single broken link turned into a multi-state, multi-day emergency operation. That's the trade-off of building the biggest rocket program in history. Every problem gets bigger too. The arm that wouldn't let go. Now the scrub. The one most people remember as a stuck pin. True, but only half the story. There's a mechanical arm on the tower called the Ship Quick Disconnect, or QD Arm. Its job is to stay locked against the ship, feeding it propellant right up until the final seconds before launch. What most people don't realize is that arm doesn't just touch the ship gently. It's under constant, deliberate pressure, pushed hard against the vehicle on purpose, so that even if something shifts during those final moments, the connection stays airtight. In the last 40 seconds of the countdown, a pin releases, unlocking the arm so it can swing clear the instant the rocket lifts off. Simple in concept. Except Flight 12 was the very first time this specific arm had ever been unpinned under real, live flight conditions with a fully loaded Starship sitting on the pad. When the pin came out, all of the stored mechanical preload, all of that pressure pushing the arm against the ship suddenly had somewhere to go. The arm shifted, barely, a fraction of an inch. But the hydraulic system watching that arm was tuned to extremely tight tolerances. Tolerances built for a moment nobody had actually tested before in a real countdown. That tiny shift tripped the limits and killed the attempt. Was the arm broken? No. It did exactly what it was engineered to do. The problem wasn't the hardware. Nobody had ever watched this specific moment happen before because nobody had ever gotten this far before. The fix arrived within hours. Overnight, engineers welded a small hard-stop bumper directly onto the ship's arm, a physical limit that stops it from displacing beyond a certain point when the pin releases. No redesign, no weeks-long investigation. A welded piece of metal installed in the dark hours before the next launch attempt. That bumper is what allowed Flight 12 to fly. The story. Everyone got wrong. This is where the real twist begins. After Flight 12, the early explanation circulating everywhere, including from this channel, was that Raptor 3's reliability was the core problem behind both the booster's destruction and the ship's engine issue. Simple story, one villain, easy to understand. SpaceX's official postmortem tells a different story, and a more interesting one, because it's actually two separate failures with two separate causes that just happen to look similar from the outside. Failure number 1. During stage separation, the moment when the ship's engines ignite while still attached to the booster, a maneuver SpaceX calls hot staging, the ship's engines lit up with slightly different timing than expected. That small timing difference pushed against the booster underneath it. The result? Booster 19's directional flip, the maneuver that turns the booster around to fly back toward the coast, ended up roughly 90 degrees off from where it should have pointed. Think about what a 90-degree error means. That's not a rocket drifting slightly off course. That's a rocket turning to face an entirely wrong direction at supersonic speed, seconds after separating from a vehicle carrying enough energy to level a city block. This wasn't a Raptor reliability problem at all. This was a software and timing interaction between two vehicles that had never flown together in exactly this configuration before. SpaceX's fix, the startup sequence, has been rewritten to be more resistant to small timing variations, so the flip points the right direction regardless of tiny differences in when each engine catches ignition. Failure number 2 is where the earlier explanation turns out to be right after all, just not in the way anyone expected. During the boost back burn, the maneuver that sends the booster back toward its landing zone, 5 of Booster 19's 33 engines failed to relight. 5 out of 33. That failure ended the boost back burn early, and once the boost back burn ends early, the booster doesn't have the trajectory or fuel margin it needs for the landing burn. The landing burn essentially never had a chance to succeed because the failure that doomed it happened minutes earlier quietly. In an engine relight sequence, most people watching the stream never even noticed. So which explanation was correct? Both and neither, depending on which moment of the flight you're talking about. The booster's flip was a hot staging and software problem. The booster's inability to land was a Raptor relight problem. Two different failures, stacked on top of each other on the same vehicle, in the same flight. There's a third piece most people never even heard about. Roughly 40 seconds after stage separation, Starship's upper stage lost one of its 3 vacuum-optimized Raptor engines. The ship kept flying. It demonstrated engine-out capability in real flight conditions, adjusted, and still hit its planned trajectory with only 2 of 3 engines running. That's not a failure. That's proof of margin. A vehicle designed to survive losing a third of its upper stage propulsion and still complete its mission is a vehicle built with buffer, not a vehicle built to fail. What actually changed? Why Thursday is different? So what does SpaceX do with all of this information? They don't just patch and hope. Every single failure gets a named specific hardware or software fix, hot staging flip error, startup sequence timing, rewritten for robustness. Engine relight failures during boost back, hardware modifications specifically targeting relight reliability, plus updated engine alarms and abort logic tuned to what a real multi-engine flight environment actually looks like, not what a simulation predicted, vacuum engine loss on the ship. described as an interconnected issue with several hardware and operational fixes already implemented and more Raptor reliability improvements still coming in future engine versions. Notice what SpaceX didn't do. They didn't say the problem was solved and move on. They admitted more improvements are still needed. That kind of honesty is rare in an industry where companies typically minimize bad news. Raptor still has work to do, and SpaceX is saying so out loud. This brings us to Flight 13 and why it carries more real risk and more real stakes than Flight 12 did. Every point of failure from Flight 12 gets tested again on Thursday. The hot staging sequence, the engine relight system, the upper stage Raptors. Nothing gets skipped. Nothing gets assumed fixed without a live retest. But there's a difference that changes the entire risk calculation. On Flight 12, the payload was 22 objects. 20 of them steel simulators built to mimic the weight and shape of satellites, only 2 of them real. On Flight 13, there are no simulators. 20 real functional Starlink 5-3 satellites are riding inside this ship. Real laser optics, real onboard thrusters, real hardware that costs real money, deliberately flown on a vehicle whose booster failed its landing burn just 1 flight ago. Ask yourself why SpaceX would take that risk. The answer says something about how confident they actually are in the fixes, not just in words, but in the decision to put real hardware on the line. You don't fly 20 functional satellites on a rocket you don't trust. Flight 13 also flies through higher dynamic pressure during ascent than any previous Starship flight. Higher dynamic pressure means more mechanical stress on every tile, every attachment point, every seam in the heat shield. SpaceX is accepting that added stress on purpose because higher dynamic pressure trajectories mean more payload capacity to orbit. A trade-off made deliberately, tested for the first time on a flight that also happens to be carrying its most valuable payload yet. To watch that trade-off play out, SpaceX scaled up its heat shield inspection program. Flight 12 flew 2 cameras, Flight 13 flies 6. Those cameras scan the heat shield in real time and transmit imagery back down, feeding directly into the process of certifying exactly how a heat shield needs to perform before SpaceX commits to flying a ship back over populated land. Every previous splashdown has happened over open ocean, specifically because nobody has fully certified the heat shield's reliability yet. The path toward flying Starship back to land, back to the launch site, back to an actual catch, runs directly through data being collected on flights exactly like this one. The bigger picture, nobody talks about. Here's a detail that deserves more attention than it got. The launch pad currently being used, Pad 2, was designed to support a launch every 60 minutes. Not every day, not every week, every hour, indefinitely. Compare that number to where the program actually is right now. 4 static fire attempts needed just to succeed once. A tower chain snapped and needed a 30-hour emergency repair. A quick disconnect arm needed a welded bumper installed the night before launch. And the design target for this pad is 1 launch every single hour, forever. That gap between where the hardware is today and where the pad was engineered to eventually operate tells you something important. This isn't a test campaign anymore. It's the early, difficult phase of building an industrial launch operation, one designed from day one for a scale that doesn't exist anywhere else in spaceflight history. The reason that gap needs to close isn't abstract. NASA's own estimates say a single crewed moon landing requires at least 15 Starship launches just to fuel an orbital propellant depot. 15 launches for 1 mission to 1 destination. An hourly capable pad isn't over-engineering. It's the minimum infrastructure needed to make that math work at all. There's a second piece of this puzzle that connects directly to what's flying on Thursday. SpaceX recently unveiled StarMind, a planned constellation of AI-focused satellites. The flagship design, called AI-1, targets 150 kilowatts of peak compute, carries a wingspan around 70 meters, roughly 2/3 the length of a football field, and needs a 110-meter deployable radiator just to dump the heat that much computing power generates. SpaceX filed with the FCC to eventually launch up to 1 million of these satellites. That number is only conceivable if the launch vehicle carrying them can fly constantly, cheaply, and reliably. The relight fixes, the heat shield data, the landing burn attempts, they're not just about proving Flight 13. They're deposits toward a constellation that size. It's not just SpaceX's own ambitions driving this. Japan's iSpace signed an agreement for 500 kilograms of payload capacity on Starship's first mission to the moon, expected as early as 2030. That deal opens the door for other companies, universities, and governments to book anywhere from a few kilograms to multiple tons on a shared lunar cargo run. The flywheel effect is straightforward. Make the vehicle reliable and affordable enough, and customers show up on their own. The question Flight 13 has to answer. Everything converges on Thursday, July 16th at 5:45 p.m. Central. Booster 20 has already fired all 33 engines for a full 25-second duration on the first attempt with no aborts. That alone tells you the static fire problems that plagued Booster 19 have, at minimum, not repeated themselves. Ship 40 has cleared its own testing. The chain that failed the tower has been replaced. The arm that wouldn't let go now has a welded bumper physically limiting its movement. The hot staging sequence that sent Booster 19 spinning 90 degrees off course has been rewritten at the software level. On paper, every documented failure has a named fix. But paper fixes and flight-proven fixes are two different things. Flight 12 proved that some problems only reveal themselves the first time real hardware experiences real flight conditions. No simulation, no static test can substitute for that. The engine relight system worked in review. It failed 5 times in real flight. The hot staging timing worked in simulation. It flipped a booster 90 degrees in real flight. That's the real stakes of Thursday, not whether SpaceX understands what went wrong, because clearly they do in granular, hardware-level detail. The real question is whether understanding a failure and fixing it on paper is enough to survive contact with an environment that has already proven it finds problems nobody anticipated. 20 real satellites, a booster with a rewritten flight computer, an upper stage flying through higher stress than it's ever handled before, and a landing attempt on a booster whose predecessor never completed one. That's what's riding on Thursday. 2 failures, 2 fixes, 1 flight to prove them. Thank you for analyzing this with us. Like, share, comment, subscribe to the Space Brief, and check the screen now.